Our home star, the Sun, is but a single star among a vast cosmic sea of roughly 400 billion stars that constitute our galaxy, the Milky Way. For our planet, its significance is immeasurable. The Sun is the engine that regulates our climate, propels the currents of our oceans, sets the cadence of the seasons, and serves as the fundamental power source for photosynthesis, the vital process that sustains all plant life. In the absence of its light and warmth, the existence of life as we understand it would be utterly impossible on Earth. This reality brings forth a captivating question. How does the Sun produce such a colossal amount of heat in its interior? And going deeper, what truly lies within our star? As the celestial object nearest to us, it has been a subject of intense study for centuries, meticulously observed and analyzed with an array of telescopes, satellites, and space probes. While it continues to hold innumerable secrets, scientific progress has granted us a significant understanding of its mechanics, including the very processes unfolding in the depths of this gigantic, incandescent sphere. If this is the kind of material you find engaging, I encourage you to subscribe to the channel and give this video a like so we can continue to investigate the enigmas of the cosmos together. To peer into the Sun's interior directly with our own eyes is a feat beyond our capabilities. Its dense blanket of gas and plasma obstructs any and all attempts at direct visualization. Nevertheless, by leveraging modern physics and complex computer simulations, we can deduce the extreme conditions that prevail inside our star. Furthermore, by examining its atmosphere and surface, we gather critical data that aids us in unlocking the mysteries of its inner regions and the very processes that fuel the great energy factory responsible for our existence. On this expedition into the heart of the Sun, we will journey through the 6 essential layers that form its structure. These layers are organized into 2 main groups. The 3 outermost layers are the corona, the chromosphere, and the photosphere. The 3 inner layers consist of the convective zone, the radiative zone, and, at the very center of it all, the core. To commence our voyage, we begin with the most external and enigmatic layer of the Sun, the corona. A solar corona, whose name is Latin for crown, is a breathtakingly expansive region that stretches for about 8 million kilometers from the Sun's surface. While it remains almost entirely invisible to the unaided eye, there are specific ways to view it. One method involves using X-ray telescopes, which can register its faint glow. However, the most spectacular way to witness it is during a total solar eclipse. At that moment, when the moon perfectly obscures the Sun's direct light, a radiant ring, the corona, materializes in the sky. Now, the corona possesses an astonishing property. It is substantially hotter than the Sun's own surface. Whereas the photosphere's temperature is approximately 5,500 degrees Celsius, the corona can soar to an incredible 2 million degrees Celsius, making it around 360 times hotter. This peculiarity defies standard thermal logic, as one would expect. The temperature to fall as distance from a heat source increases. The exact reason for this is not yet completely understood, but the leading theory proposes that the Sun's magnetic field plays a pivotal role, creating powerful storms of energy that heat this region to temperatures that are difficult to comprehend. If a person were ever exposed to such conditions, their existence would be extinguished in less than a fraction of a second. Situated just beneath, the corona is the Sun's second outermost layer, the chromosphere. This region is positioned between the corona and the photosphere, serving as a form of transition zone between them. Despite being significantly denser than the corona, it remains exceedingly hot. The chromosphere has a thickness of roughly 2,000 kilometers and is made up of towering columns of incandescent gas that bring to mind a vast forest of fire. These dynamic structures are known as spicules, and they can surge upwards to heights between 3,000 and 8,000 kilometers before collapsing. Their existence is fleeting, with a lifespan lasting only 5 to 10 minutes. It is thought that they are launched from the solar surface at speeds reaching 20 kilometers per second, shooting up into the chromosphere. A distinctive feature of this layer is its reddish color, which occurs because the hydrogen within the sun emits red light upon reaching extremely high temperatures. In terms of its own heat, the chromosphere registers temperatures near 3,700 degrees Celsius. However, as it approaches the corona, the temperature rises sharply, a phenomenon that remains an active area of scientific research. But this is merely the start of our solar exploration. As we venture deeper, we will uncover even more captivating details about its internal structure and the mechanisms that establish it as the definitive energy source for our solar system. Accompany me on this descent into the very core of our star. Are you prepared to discover the next layer? It is now time to plunge much deeper. We have arrived at one of the most compelling layers of the sun, the photosphere. This is the lowest region of its atmosphere, and you might know it more commonly as the solar surface, because it is the part of the sun that is visible from Earth. Its name is derived from ancient Greek and translates to sphere of light, a fitting title as this is where the majority of our star's radiant energy is broadcast into space. The light that departs from the photosphere requires about 8 minutes to traverse the 150 million kilometers to reach our planet. Its temperature fluctuates slightly, but it generally hovers around 5,500 degrees Celsius, a figure that is now the established standard for the sun's temperature. We often refer to the photosphere as the sun's surface, yet it is not solid like the surface of a rocky planet. Instead, it is a turbulent, roiling layer of incandescent plasma, approximately 482 kilometers deep. If one could theoretically fall into this layer, they would find no solid ground to stand on. They would simply sink into a boundless ocean of seething plasma, though realistically, the individual would be vaporized instantly. The energy and heat that bubble up from the photosphere have journeyed for millions of years from the sun's core before they finally break free and escape into spacedot within the photosphere. We can observe brilliant structures with distinct geometric patterns which are formed by the ceaseless motion of plasma. These are called solar granules, and they manifest due to heat being transferred from the deeper layers through a process known as convection. Alongside these granules, we also find sunspots, cooler, darker patches that appear when the sun's powerful magnetic fields breach the surface. Sunspots appear to drift slowly across the photosphere, and it was the study of their movement that enabled astronomers to deduce that the sun rotates on its own axis. But our journey doesn't stop here. It is time to press onward into the inner layers of the sun, starting with the first among them, the convective zone. In this region, heat is transported by the physical movement of plasma, a process that creates the solar granules seen in the photosphere. The zone's name comes directly from this heat transfer mechanism known as convection. In the deepest parts of this zone, temperatures hit 2 million degrees Celsius, but as the plasma rises toward the surface, it gradually begins to cool. The motion of plasma in the convective zone can be likened to a pot of boiling liquid, with hot bubbles carrying energy upward. The density here is comparatively low, which allows light particles, or photons, to be carried along and converted into heat. Yet, there is still more to uncover, and as previously noted, the deeper we proceed, the more extreme the conditions become. Lying beneath the convective zone is the radiative zone, a region where energy from the core is slowly carried outward in the form of light photons. Its name is derived from the process of electromagnetic radiation, which is the dominant form of energy transport in this layer. While it is not as dense as the core, it is still compact enough to cause photons of light to collide ceaselessly with nearby gas molecules, significantly delaying their journey to the surface. According to NASA's research, a single photon of light can take over 100,000 years to travel from the core to the photosphere. Once it finally breaks free, however, it needs only 8 minutes to reach Earth. We now arrive at the very heart of our star, the core. The Sun's core is a colossal nuclear fusion reactor, where unimaginable temperatures and pressures force hydrogen atoms to fuse together, forming helium and releasing an extraordinary amount of energy in the process. It is estimated that the temperature in this region soars above 15 million degrees Celsius, and the energy liberated in a single second is greater than that of 1 billion atomic bombs, exploding simultaneously. We have reached the epicenter of hydrogen. The Sun, the source of all energy that streams to Earth. The light generated here will embark on a journey of hundreds of thousands of years to reach the solar surface. If we could somehow arrive in this region, we would be imprisoned here for eternity, powerless to escape the extreme conditions. As we are not photons of light, capable of traveling at 300,000 kilometers per second, escaping this place would take us countless millennia. But our mission is complete. We have now explored in detail the structure of the Sun and the magnificent mechanism that allows it to shine so brilliantly in the cosmos.